All right, so in this lecture, I'm going to talk about reaction runaway. So we're basically just going to go through this set of notes. You can go ahead and read it. You don't have to listen to me go over it, but if it's helpful to you to have me explain it, then by all means, listen to this video. But there's no filling in, and there's no gaps in this lecture. I just decided to write it all out. So reaction runaway, there's a risk whenever the heat generated term is greater than the heat removed term. And so this is because reactions give off a lot of heat. So we've already looked at delta H of reactions, heats of reactions, and showed that they are a lot larger than heat given off from other quantities. For example, if I condense water vapor into liquid water, the heat that's given off in that reaction is a lot, or in that process is a lot smaller than the heat that is given off in a reaction. So there's a lot of potential energy stored in the chemical bonds of chemical species. So when we break and form chemical bonds, there's a lot of heat involved. Because of that, it can be very hard to control that heat generated. So one of the largest anthropogenic types of disasters results from malfunctions of chemical reactors. So as chemical reactions engineers, it's very important for us to understand this. So what happens in a runaway reaction, if the heat removal term is not sufficient to compensate the heat generated, then the heat will increase the temperature. The temperature increases the rate constant, which increases the rate. This increases the heat generated term even more, so the heat generated term is eventually increasing itself because it's a function of this reaction rate term. So once the heat generated term is exceeding the heat removal, it can be difficult, if not impossible, to control. And reaction runaway happens when it is no longer possible to control the heat generated term using the heat removal strategies. This happens when the temperature of no return is reached. So the temperature of no return is the temperature at which the rate constant is so large that reaction runaway cannot be prevented. So the temperature has now gotten to some point where the rate of some reaction is going so quickly that it does not matter what cooling system we throw at it, it's not going to prevent the heat generated from increasing rapidly, and hence the temperature. So some everyday examples of reaction runaway. So the lithium cell phone battery fires, that's a runaway reaction. So basically what happens, there has to be a manufacturing flaw there, but if there's a manufacturing flaw and heat is added, or too much heat is added, for example, by overcharging, or maybe you left your cell phone in the sun, basically that's fueling this reaction, which runs away out of control and causes a fire. Another one is global warming. So when we emit greenhouse gases into the atmosphere, this causes the Earth's temperature to rise. As the temperature rises, things like forest fires are more common. For example, the permafrost melts. When those two things happen, they release more greenhouse gases into the atmosphere, CO2 and methane, for example. That contributes even more to the temperature increase, which in turn causes more releases through things like more forest fires or more, gases trapped in ice that's melting, being released, and the temperature keeps increasing and so on. So it's like this, the reaction itself eventually causes the temperature to rise that fuels the things that started it in the first place. There's several examples of runaway reactions in the textbook, so these are listed here. I'll let you read through those in detail. Basically what's going on, and I'll give you some highlights. So this example 12.7 is a PFR. There's several features that cause the reaction to look like it's running away. Basically what happens is the temperature spikes, and it doesn't matter which heat mitigation strategy is employed. We can't prevent the temperature in the reactor from spiking to at minimum 840 Kelvin, which is really hot. In this particular example, the temperature comes back down. So when the temperature comes back down, it's not reaction runaway because the heat mitigation strategy though it allowed a spike, it eventually brings it back down. The problem here is that this particular example, there's two reactions there. That's the only two reactions that we're modeling. Usually a runaway reaction is caused when the reactions that are present under normal operating conditions, so the ones that are being carried out under the design conditions, those get out of control and cause the temperature to get hot enough that then some other reaction sets in. So in the examples that we'll see after this one, something else is happening. So it's often not the reaction that is designed for that is causing the reaction to run away. It might start the process, but then once that process is started, other reactions that were previously latent start happening. So examples of reactions that could come into play that weren't originally in play, new reactions between the reactant and product species. You could have atomization or decomposition of the reactant or product species. For example, if one of these species were methane and the temperature got really hot, you can imagine methane decomposing to carbon plus hydrogen gas, or even atomizing to carbon plus atomic hydrogen gas. This is going to give off a lot of moles of gas, so 1 molecule of methane going to, in this case, 3 moles of gas, or in this case, 5 moles of gas, and that, of course, increases the pressure. You might think, well, why would vapor, what is carbon gas? Why is that even a thing? But under very hot temperatures, we can cause the bonds in the methane molecule to break. That is possible, and it's also possible for carbon to be in its gaseous form when the temperature gets really hot. So it's a reaction that under maybe normal operating conditions, you wouldn't think, oh, I have to worry about methane. Methane's a very stable molecule. I don't have to worry about it decomposing or atomizing, but at very hot temperatures, it's certainly a concern. Another would be if this were a solvated reaction, any of the species could start reacting with the solvent, or the solvent could atomize or decompose. Even inert species. So say that you were flowing in an inert species, and that inert species was molecular nitrogen. At very hot temperatures, molecular nitrogen gas can atomize into 2, so every mole of, or 1 molecule of N2 gas can atomize into 2 moles of atomic nitrogen gas. And again, that's not something that you would consider to happen at a low temperature, but at these hot temperatures that can be achieved when the reaction starts running away, that is possible. And when something like that happens that's outside of the design considerations, that's exactly the scenario where a heat removal strategy is going to be insufficient, because it wasn't, such things like that tend to not be planned for. So our job as chemical reaction engineers is to think about all of the processes like that could happen, and make sure that we have heat and pressure mitigation strategies in place in case something like that happens. Another example is problem 13-2b. In this case, it's a CSTR reactor that's being fed a molten ammonium nitrate and water solution. In the reactor, the solution decomposes to form gaseous nitrous oxide and steam. Then this reactor ended up exploding. What happened was that there was the control features identified that there were pressure fluctuations inside the reactor, and so the feed was shut off. However, a main source of heat removal was this conversion of the liquid reactants into gaseous products. So that requires a lot of energy must be absorbed by those chemicals in order for the liquid phase to be converted into the gas phase. So when the heat was shut off, that part of the heat removal strategy was no longer there. So by shutting off the feed, what essentially happened was a significant source of heat removal was also removed. So thinking about this is an example of why it's important to identify what exactly contributes to heat generated in heat removal terms, because we certainly don't want to remove heat removal terms in a reaction that is generating heat. Example 13-2 is Monsanto plant explosion. So in this case, the heat exchanger failed for 10 minutes. This was a normal thing, so the heat exchanger and this reaction would often fail for 10 minutes, but the operators would would notice that and turn it back on. However, the reactor had recently been filled too much, so someone from the business office walked by and said, why is that reactor only operating at only 1/3 capacity? Why don't we increase it to full capacity and make more money? A problem with this is that it's designed to operate at 1/3 full. The heat removal system was designed such that it was only operating at 1/3 full. So when the reactor was filled more, the heat removal system was inadequate to account for one of these 10-minute heat exchanger failures. Because of that, the heat generated term got to be significant. This caused the temperature to rise significantly, and again, it was one of these scenarios where there was buildup of gas, which caused an explosion. Interestingly here, so a design feature here was that if the pressure inside the reactor got to be too high, then a rupture disk would burst, and that would cause the water in the reactor to vaporize. So there's liquid water in the reactor that cause it to vaporize, and that would serve as a heat removal strategy. So the heat would have to go into that. So the water would need to absorb that heat in order to vaporize. So you can think that this is, maybe a reason why under design conditions the reactor was only to be 1/3 of the way full, so that there was room for there's headspace in order for this water to be able to vaporize if needed. So you can imagine this being, I don't know this for sure, but you can imagine this being a safety feature. So it was meant to have only 1/3 of that was meant to have liquid in it. And, so overfilling it presented multiple problems. Example 13.6 is the T2 example. So that's also in one of the videos that you hopefully watched before getting to this lecture. In that case, there was again a heat exchanger failed. As the heat exchanger failed, one of the normal reactions in the reactor produced hydrogen. When the heat exchanger failed, this caused the heat generated term the temperature to increase due to the fact that the heat generated term wasn't being compensated by the heat removal term. This caused even more production of H2. As the temperature increased, one of these latent reactions came into play. So the solvent started to atomize. So it was an organic solvent. The temperature became hot enough that that solvent started to break down into its components. So that particular reaction had a very high activation barrier, so the rate under normal operating conditions was very, very small. It was something that you didn't really have to worry about. As the temperature went up, then the rate became appreciable regardless of the high activation barrier. So at some point, that rate of that solvent decomposition reaction was appreciable, and so now that reaction is occurring. That reaction, since it wasn't under the normal design scenario and no one had thought about it, the heat removal strategies were, completely insufficient for mitigating the heat of that reaction. This caused even more production of H2 that caused the pressure and the temperature inside the reactor to increase, and the reactor eventually exploded. So that brings us to a key point. Reaction runaway is often caused by reactions that are latent under normal operating conditions, but which come into play during a runaway scenario. These reactions have high activation barriers and hence negligibly small rates under normal operating conditions, but when the temperature approaches the temperature of no return, their rates are appreciable. These reactions are exothermic and hence contribute to the heat generated term. Once they've set in, they are nearly impossible to control. Hence, it is imperative to know, 1, what reactions could occur given the chemicals in the reactor. This includes inerts, solvents, etc. So what could occur beyond just the reactions that are occurring under normal conditions? What else could occur? So I have these chemicals. Let's pretend that anything could happen. What would happen? And then 2, we need to know also the temperature of no return, because we need to be operating well below that. So we don't want, normal process fluctuations, heat exchangers failing for 10 minutes. we need to be well, even if any of those things happen, we need to be well below the temperature of no return. So even if the reaction you're carrying out is endothermic, reaction runaway is still a concern. So remember, it's not just the reactions that are part of the design of equations, it's every possible reaction given the chemicals involved. So even an endothermic reaction where you have to add heat to the reactor, imagine then that your heat added term becomes or overtakes the heat consumed term, right? So then you're adding heat, the temperature gets high enough, and something else within the reactor starts happening. So it's not just related to exothermic reactions. It's certainly not limited to just the reactions that are part of the design. It's anything in the reactor that can cause or that can start producing heat and causing the temperature to increase. And we as chemical reaction engineers, it is our responsibility to be cognizant of all of that. For estimating the temperature of no return, there's experiments that can be used to do that. Basically, it's a calorimetry experiment in a sealed vessel. So the vessel is sealed to mass flow, so no mass can come in or out. And it's adiabatic, or as adiabatic as possible. What happens is you add a very small amount of your reaction mixture into this very small vessel, and you increase the temperature. And as you increase the temperature, you monitor the temperature. So you watch for a temperature spike. And the way that this is possible is that the amount of reaction mixture is very small, so the reaction extinguishes quickly. But that allows us to investigate as a function of what's the reactor temperature as a function of the temperature inside the reactor. So where does that go as I'm increasing, I'll have a linear region where, an increase in temperature just results in an increase in temperature. But then I'll have a spike where an increase in temperature caused some other process to set in that would cause the reaction to run away. So I perform that experiment, and I have an estimate of what my temperature of no return is, and then when I select my operating conditions, I set it such that I never get anywhere near that temperature of no return. Another risk of reaction runaway is due to scale up. So when we think about designing an industrial process, oftentimes we start at the bench scale. By bench scale, I mean, on a laboratory bench top. So for example, in a beaker. And of course, what happens in the chemistry that happens in that beaker is similar to what would happen in the industrial scale, but it's not identical. So there's more concerns at the industrial scale than at the bench scale because it's a lot larger. So when you take senior design, and maybe even in your career, one of the things you'll do is you'll look into the literature and you'll find people who have carried out the reaction that you want to carry out in a laboratory experiment. These people will usually have used a bench scale batch reactor to carry out their chemistry and to learn something about the chemistry. And sometimes they'll give you an estimate of a residence time for that reaction. Now that estimate of the residence time is based on their bench scale experiment. So if you want to scale up, then you can estimate using their residence time what reactor size, for example, you would need to carry out the production rate that you want to achieve in your industrial scale reaction. A problem here is that the surface area to volume ratio of your bench scale reactor is a lot larger than it will be for your industrial scale reactor. So the scale-up process gives you an estimate, and in fact, it's useful as a first pass at what size reactor you're going to need, but it is insufficient and inadequate for your final answer. For your final answer, you need to go through and solve the detailed material and energy balance equations that take into account the difference in surface area to volume from the bench scale to the industrial scale reactor. In fact, a key risk of reaction runaway is scale-up that does not adequately take into account the change in surface area to volume ratio in going from your smaller reactor to your larger one. And this is especially true given that industrial scale reactors can be very large. So think about the size of a jacuzzi being a small industrial scale reactor. Some industrial scale reactors are much larger than that, significantly so. So a key point here is that using residence time from a bench scale experiment to scale up a reactor is only an estimate, does not substitute for solving the full set of material and energy balance equations. And another key point, which we hit on above, is that just solving the set of material and energy balance equations for the desired reactions or the known reactions or the reactions that are going to occur under normal operating conditions is also insufficient. You need to look for and think about the other reactions that could occur given the chemicals that are available and also the conditions under which the reactor is operated.